recording. I hope you guys are doing fine. Today we are going to start talking about wave optics. Let me go to the presentation or slideshow. I'm going to do it a little bit differently today, see how it works. So as I mentioned, today we are going to start talking about wave optics. In the previous chapter, we actually saw some of the different phenomena that we could actually use ray optics in order to see what happens. When I say ray optics, I mean that we assume that light travels on a straight line. And we could use that to interpret how reflection or refraction of light happen, and then use those to see how, for example, mirrors and lenses form images. But there are other situations you cannot use ray optics in order to explain them. For example, if you look at bubbles and then the light rays are coming in, there is no way that you can use ray optics to explain what is happening here. If you have foam, for example, light is going to get reflected by this surface, but then you see some kind of different colors coming off this foam, which is which you cannot explain using ray optics. So what we are going to do today is to see the fundamentals of wave optics, and then how we can use to describe some different phenomena uh, that we would be unable to explain if we just wanted to stick to array optics. Now, in the video you watched before this lecture, I reminded you some of the things that we saw and learned in Physics 1. We talked about the interference of the waves and what the conditions were to have a constructive or a destructive interference. So let's just look at one of those slides that we had. So if we had two sources, for example, if we have two sources like source 1 and source 2, these sources, they could actually be source of sound waves or light waves or any other type of wave that we can imagine. These two generate waves in all possible directions. Now, if you have, if you sit, for example, at A, uh, at any given time, there are two waves coming at you. One of them is coming from source 1, the other one is coming from source 2. Now, that happens for actually for at any other point. Now, if the path difference between the two waves is a multiple of the wavelength, delta x is the path difference. That's the difference between the distances traveled by those two waves. If that path difference is a multiple of the wavelength, that means it's 0 or 1 lambda or 2 lambda or 3 lambda and so on. Then you are going to see a constructive interference. These two waves actually help each other out. You have a bigger wave at that point. But if the path difference between the two waves is uh, m plus 1/2 times lambda, m plus 1/2 could be just 1/2 or 3/2 or 5/2 and so on, then you are going to see a destructive interference where the light rays or the waves in general cancel each other out. Now, let me tell you that this you can use if the phase difference between the two waves is just a result of the path difference. In general, the formula that you have to use to determine if the interference is constructive or destructive is the phase difference between the waves. And this is something that we are going to use in the next lecture when we talk about interference as a reflection. So in that case, you have to use the more general formula where it says interference is constructive if the phase difference is an even multiple of pi, and it's destructive if the phase difference is an odd multiple of pi. So these would include like pi, 3 pi, 5 pi, and so on. And this would be 0, 2 pi, 4 pi, and so on. And note that there is a relation between phase difference and path difference. If the phase difference is the result of the path difference, you can relate those uh, through this formula. If you have path difference between the two waves, then if you replace delta x by whatever you have, then you are going to get the phase difference between those two waves. This is another thing that I'm going to use. This formula is another formula that I'm going to use in the next lecture when I talk about the interference as a result of reflection. But before that, let me tell you that in 16th and 17th century, there were two competing views on light. One of them was the ray optics. Some scientists thought that light was traveling on a straight line, and they could actually use that to describe like reflection and refraction of light waves. But then there were some other scientists who proposed the idea of wave for light, and one of them was Huygens. He had a principle which is called Huygens principle. He assumed that light was traveling as a wave. We could actually, the two simplest way to imagine the propagation of light would be this way, where we call it a plane wave, or a spherical wave like that. When I say plane wave, the light rays are going in this direction, and they are all parallel to each other. The light rays are, but here the light rays are diverging from one another. And when you draw surfaces perpendicular to those diverging light rays, you're going to get spheres. In this case, the lights are parallel to one another. And when you draw planes perpendicular to those light rays, you get just flat planes. Now, according to Huygens' principle, each point on the wavefront, wavefronts are these surfaces that I have drawn. So this is the wavefront for a plane wave, and this is the wavefront for a spherical wave. Now, according to Huygens' principle, each point on the wavefront acts like a new source of light or wave that generates a spherical waves. So when you look at this point, which is on the old wavefront, this point acts like a new source for the light, and it's going to generate uh, spherical waves. This point does the same thing. This point does the same thing. And then after you wait for delta t seconds, the new wavefront is the one which is tangent to all of those circular wavelets, these guys that were generated at these new sources. The same thing happens here. So this point becomes a new source. It generates new light rays. This source becomes a new source, generates light rays, circular or spherical if you go to 3 dimensions, light rays and light waves. And then the new wavefront is the one which is tangent to all of these old, not old, it's these circular wavefronts generated by each source that I have here. This is Huygens' principle. We don't need to know the details, the mathematical details behind that. It's much more complicated than what I just explained here. The only thing that we need to learn here and carry it over to other material that we are going to use is this fact that if you have a light, if you have a wavefront of light, each point on the wavefront is going to act like a new source of light. And we are going to use it in explaining some interesting phenomena. For example, today I'm going to use it to explain how Young's double slit experiment actually works. So that's the only thing that I want you guys to carry it over to other material. Let me tell you that we can actually use Huygens' principle to prove the law of reflection, which says the angle of reflection is equal to angle of incidence. And also we can use it to prove Snell's law, which was the law governing the refraction of light. But again, that's going to be very, very difficult to do. It's not as easy as what we did in the ray optics. I'm not going to do that. I'm just going to use this principle to explain a few different phenomena related to wave optics. So let's look at the Young's double slit experiment. Let me tell you what that is. So you have a source. This source generates spherical waves. That means you have light rays going at all possible directions, and the wave fronts are going to be like circles. You have a screen here. The screen blocks the entire light ray, except you have created two very, very narrow slits at on this screen, and let's assume that the distance between the first slit to the source is equal to the distance between the second slit to the source. And then you have another screen here that you can see what's going to be happening on this screen after this source starts emitting light. If the ray optics was correct, what you would expect to happen is this, that uh, two light rays, one going through the first slit and the second one going through the second slit, are going to illuminate this screen. So you are going to see a bright spot here, and you are going to see another bright spot here, and then everywhere else on this screen you expect to be dark if light was if ray optics was correct, if light was traveling on a straight line. That's what you would expect if ray optics was correct. But if you use a Huygens principle, then according to Huygens principle, each slit is like a new source for the light. So when the light gets to this point, this slit becomes or acts like a new source, and it generates light rays in all possible directions. And the second slit does the same thing. So if you have a screen here, at any point on the screen, you are going to get two light rays coming. One from the first slit, because now this is a new source that generates light in all possible directions, and one which is coming from the second slit. So you are going to get two light waves coming at that point on the screen. I don't have the screen here, but I mean, if I had that screen, that would be something like this screen here. Now, at any point on that screen, you are going to have two light waves, one coming from the first slit, the second coming from the second slit, and those two light rays now could interfere constructively or destructively. If they interfere constructively, what you are going to see is a bright spot or bright band. They usually call them fringes. And if they interfere destructively, you are going to see a dark spot or dark fringe. So if I want to show it differently, this is what's going to happen. These are the two slits. And then you look at the screen here, and what you see is completely different than what you would have expected if ray optics had been the correct theory describing light. What you would see is this, a series of bright and dark fringes following one another. You can say at the locations that I have a bright fringe, the two light rays coming from S1 and S2, these two slits interfered constructively, and for those dark fringes like this and this, the two light rays coming from these two slits uh, interfered destructively. So let's see if we can formulate this. Before that, again, let's see what's happening here. I have two slits, S1 and S2. They generate light rays in all possible directions. These two light rays reach at different points on this screen. If you look at P P is a point exactly halfway between these two. In other words, the distance that the first light ray travels to get to this point is equal to the distance that the second light ray travels to get to this point. That means in this case, for this point, the path difference is 0. And since the path difference is 0, there is no phase difference between the two waves. As a result, these two waves are going to interfere constructively. So you expect to see a bright fringe, a bright fringe at that center. That a bright fringe actually is usually called the central bright fringe. And uh, it usually has the most intensity. It usually is the brightest. If you look at a different point, let's say this point, as you can see, the light coming from S1 actually travels more distance compared to the light coming from S2. Let's assume that for this specific point, the path difference between these two is exactly one wavelength. You can actually count the wavelength here that you have for the second wave and the first wave, and you see that the difference between the two is exactly one wavelength. The difference, the path difference is one wavelength, and that is the condition to have a constructive interference. So at this point, you are going to see another bright fringe. But if you go halfway between P and Q, you remember at P we had a bright fringe. At Q, we also have a bright fringe. But if you go point halfway between the two, let's say at R, then you can see that the light that is the two light waves that come together here, they have a path difference of half of a wavelength. And that means at that point, they are going to actually interfere destructively. And that means that you are not going to see any light at that point, as a matter of fact, because the two light waves uh, uh, cancel each other out and the interference is destructive. So you are going to see a dark fringe at that point. There is another way to see that. Again, you have these two slits here, and then each slit is going to act like a new source. These are light rays coming from each slit. And then if you look at different points, at this point, you are going to see a maximum, another maximum here, another maximum here. At this point, the path difference is exactly 0. At this point, the path difference is one wavelength. At this point, the path difference is two wavelengths, and so on. Also, between any two bright fringes, you have a dark fringe where the path difference is m plus 1/2 times lambda. So for example, here the path difference is lambda over 2. Here the path difference is 3 lambda over 2, and so on. And this is what you are going to observe for this situation. Now, if you look at, if you want to formulate this situation and find a couple of different formulas that we can use in order to do some examples, let's assume that I have this situation here. I have two slits, S1 and S2, and then I'm looking at the point P on the screen. Let's look at some of the quantities that are important for me. I have little d here, which is the distance between the two slits on the screen. I have L, big L, which is the distance between the slits and the screen that I view those bright and dark fringes. Then I have another quantity which is denoted by Y, and that's the distance between the point of observation and the center of the screen. Center of the screen is the location where you will see the central bright fringe. So I have Y, I have D, I have L. I also have these two light rays coming together at P. The first one travels a distance of R1. The second one travels a distance of R2. One thing that I should mention is in the lab, usually this L is much, much, much greater than D. In other words, the viewing screen is much farther than the distance between the slits. So this picture is not in a scale at all. Uh, if D was this much, then L should be a few meters. You wouldn't be able to see it on the screen. And now, if that's the case, since these two light rays are going to meet each other very far away, when you look at them here, as I have drawn here, when you look at them very close, they appear to be almost parallel to one another because they are supposed to meet each other very, very far away. So at this area, when we are very close to the slits, these two light rays almost appear to be parallel to one another. And as a result, you can draw a line here which is perpendicular to this one, and then you can say this small thing that I have is literally the path difference between the two. That's because from here to the screen would be equal to from here to the screen. So from this point to the screen would be R1. So this is basically the path difference between the two. And then you can use the equation for sine theta in a triangle. Sine theta would be the opposite side divided by the hypotenuse, which is theta. Remember, this is 90 degrees. So then I have a relation for the path difference for the two light rays coming together at P. So if you know the angular position for this point P, how do you determine that angular position? You connect this point to the center of this, or the halfway or the midpoint between the S1 and S2. So you connect P to this point, you find this angle, theta, and then you also know what D is. So if you calculate D sine theta, that is going to be the path difference between these two light rays coming together at P. So that's one important formula that we have. But now this path difference could be a multiple of wavelength, or it could be m plus 1/2 times wavelength. If the path difference is m lambda for m equal to 0, plus minus 1, plus minus 2, and so on, then you are going to have a bright fringe. So solving this equation will give you the angular position for the bright fringes. But if the same path difference, which is d sine theta, is equal to this m plus 1/2 times lambda, then you can find the angular position for the dark fringes. So again, it doesn't matter if you are looking at the bright or dark fringes, the path difference is always d sine theta. But if d sine theta is equal to m lambda, that means the path difference is equal to m lambda, and that is the condition for constructive interference. So you are looking at bright fringes. And then if the path difference, which is d sine theta, is equal to m plus 1/2 of lambda, then you are looking at the dark fringes. You can actually relate these formula to the position of that point P, y, instead of just angular position. So let's see if we can do that. Coming back to this triangle that I have here, if you look at this triangle now, this one, you can write tangent of theta here. Tangent of theta is going to be y over L. So you can say y is equal to L tangent of theta. I use the fact that tangent of theta is the opposite side divided by the adjacent side. Now, again, if you use the fact that this L is very, very far, this angle theta is usually going to be a very small angle. it's less than 6 degrees. And some of you might have learned this in other courses that for very small angles, you can replace tangent of theta by sine of theta. So you can say y, which is equal to L tangent of theta, for the cases where theta is small, can be written as L sine of theta. So again, you can usually do that in de Young's double slit experiment because L is much larger than D, and as a result, this angle is going to be very small. So you can usually replace tangent of theta by sine of theta. So Y is equal to L sine theta. Now, note that you have d sine theta for the bright fringes to be equal to m lambda. Now you can replace sine of theta from here by y over L. So you can replace sine of theta by y over L, and then you can solve this equation for y. Then y for the bright fringes is m lambda L divided by d. And this is the formula that I'm going to use to do several of the problems. Again, m can be 0, plus minus 1, plus minus 2, and so on. For the dark fringes, you're going to do the same thing. You're going to say d times sine of theta for the dark fringes is equal to m plus 1/2 times lambda. That's the formula that you saw in the previous slide. Now, again, replace sine theta by y over L, and then you are going to get this formula for the dark fringes. Y for the dark fringe is lambda L over d m plus 1/2, which is uh, where m can be 0, plus minus 1, plus minus 2, and so on. Now, in order to see what I mean by this, let's look at a situation where I am just looking at the screen and where the dark and bright fringes are. So this is what I have here. This is the screen. I know that for the bright fringes, the y location ended up to be m lambda L over d. For the dark fringes, the location turned out to be m plus 1/2 times lambda L over d again. These are the formulas that we saw in the previous slide. Let me show them to you. These are these two formulas. I have just moved m and m plus 1/2 to the other side of this equation. So I have the location for the bright and dark fringes. Now let's see what I mean by m. So you look at the very brightest one here, and that's gonna maybe here. That's gonna be your m equal to 0. That's m equal to 0 for the bright fringes. And for that, if you replace this m by 0, you are gonna get y0 to be 0. So that means that the central fringe is exactly at the center of the screen. But then you look at this fringe, that bright fringe, for that one, m is 1. M is 1 for this one. That means you have to replace this m by 1 for this guy. So you are going to get y1. That's actually y bright 1, but I have dropped the b. And it's going to be 1 lambda L over d. Then you can go to this one. For that one, for that one, m is equal to 2, and then y2 becomes 2 lambda L divided by d. You can keep going in this direction. How about if we wanted to go in this direction? Well, for this one, m is going to become minus 1, and then y is going to become minus lambda L over d. You can go to minus 2, minus 3, minus 4, and so on. That will take care of the bright fringes. How about the dark fringes? In order to find the location of the dark fringes, you have to use this formula. So you start with this one, this dark fringe, which occurs between this one with m equal to 0 and m equal to 1 for the bright fringes. For this one, if you want to use the dark fringe equation, m is going to be 0. So m is 0, you put m equal to 0, and you are going to get y to be lambda or L over 2d. That's y prime 0 prime here. Instead of writing yd be 0. I am using prime for the dark fringes. Then I go to the next dark fringe here. The next dark fringe would be associated to m equal to 1. So, but this m is for the dark fringe equation, so you put m equal to 1 here, and that's going to be 3/2 of lambda L over D. Next dark fringe, this one, you you guessed right. M should be 2 for this one, and the location is going to be 5/2 of lambda L over D. How about if you go in this direction? Of course, you can do that. For this one, M becomes, as you can imagine, -1, and then the location is going to be minus lambda L over 2D, and so on. So this is how you label these bright and dark fringes uh, by m's, and then once you have m for a bright fringe, you can use this equation to find its location, and if you have m for a dark fringe, you can use this equation to find its position. Now, one thing that you can see is when you go from any dark fringe, any bright fringe to its adjacent one, or any dark fringe to its adjacent one, the distance between these two is the same. The distance between these two is lambda L over D. The distance between these two is also lambda L over D if you subtract these two. So you can say the separation between two adjacent bright fringes, or the separation between two adjacent dark fringes, is lambda L divided by D. And finally, you can actually assign some kind of width to these fringes. It's not actually, the statement that I'm going to make is not generally correct. This is just an approximation, but this is the approximation that we are going to assume and use in this course throughout. So I'm going to assume that all of these bright and dark fringes have the same width. This is not correct. As you can see in this picture, actually, when you move away from the center, the bright fringes fade away. They are disappearing. But let's assume that as far as we know, as far as we care, these fringes, dark and bright, all have the same width. So what I'm saying here, for example, from here, the center of the central fringe to the center of the first bright fringe, where the distance is this, I just told you, you have half a width, I was here, half a width for the bright fringe, one full width for the dark fringe, and then another half width of the of this bright fringe. So this distance is equivalent to 2 times width of a fringe. As a result, you can say width of each fringe is equal to lambda L divided by 2D. Now, again, let me try to explain it here. Maybe it's a little bit hard to see, but maybe I can use a pen. So this distance that I have here, lambda L divided by D, is the distance between here and here, the center of this fringe to the center of this fringe. Now, from here to here, how many width do I have? Assuming that all the widths are the same. I have 1/2 of the width of this bright fringe. Then I have one full width for the dark fringe. So far I have 1.5. And then I have another half for this bright fringe. So I have 2 full width from here to here, and that's lambda L divided by D. So you can say width of a fringe, it's lambda L divided by 2D. Okay, so that's basically all we need to do some examples. And now what I'm going to ask you to do is to go to a Nearpod, and let me actually go there myself first and enter the code CUGLK. CUGLK. The first question is this: if the distance between the slits is doubled in Young's experiment, what happens to the width of the central maximum? Okay. Uh, so I'm going to move to the next question on the Nearpod, but before answering that question, let's see what the answer to this question is. As I mentioned here, the formula for the width is lambda L divided by 2D. I have told you what L is. L is the uh, distance between the screen and the slits. D is the separation between the slits, and lambda is actually a wavelength. What you have done, uh, you have doubled the distance between the slits. You have doubled D, which is in the denominator for this formula. So if you double the denominator, what happened to W? Is going to be halved. So the correct choice is C. Let's look at the second question. A Young's double slit experiment is performed with three different colors of light: red, green, and blue. Rank these colors by distance between adjacent bright fringes from smallest to greatest. We had a formula for the distance between the adjacent fringes. Now you have to rank these. The only thing which is different between red, green, and blue is their wavelength. And let me remind you that if you remember from the spectrum, the red light had the longest wavelength, while the blue one was the had the shortest. Of course, violet actually had the shortest, but violet is not here, so that means blue is going to have the shortest wavelength. Okay, very good. Several of you, 72% of you actually give me, well, 77 now, gave me the correct answer. So as I mentioned, the formula is lambda L over D. The one with the smallest wavelength is going to have the smallest distance between the fringes. So since blue has the smallest wavelength, is going to be the smallest one. Then it's green, and red, which has the longest wavelength, is going to have the longest or the largest distance. So the correct choice again is C. What do you think about this one? In a double slit experiment, when the wavelength of the light is increased, what happens to the interference pattern? This is like an interference pattern, and the one with and in this direction actually shows us the intensity. So wherever the intensity is high, like here and here and here, you have a bright fringe, and at these locations you have a dark fringe. So the question is, what happens to this pattern if you increase the wavelength of the light you are using? Okay, very good. I'm going to move on. But here, again, you can use the fact that width, that's one of the ways to look at it. Width is lambda L divided by 2D. If you increase the wavelength, width is going to increase. So each fringe is going to have a bigger width. And as a result, this whole thing is going to spread out. So the correct choice is A. Now let's look at this one. In a double slit experiment, what path difference have the waves from each slit travel to give a minimum at this position? So if you remember that we had two light rays, they were coming from two different slits. The question is, what is the path difference between these two light rays at this location, assuming that this with the highest intensity is the central fringe? Okay, I didn't get that many correct answers for this one. Half of 50, more less than half 50%. Let me tell you that we know for dark fringes where we have minimum, the path difference is m plus 1/2 lambda. So how can I find the path difference for this point? If you remember the way that I labeled these, you can say, okay, this is m equal to 0. This one is m equal to 0 for the dark fringes. This is m equal to 1. This is m equal to 2. And that means this is going to be m equal to 3. And if that is 3, then delta is going to be 3 plus 1/2 or 3/2. Oh, no, not 3/2, 3.5 wavelength. So that is the path difference between the two waves coming to this point. The correct choice is D. Now let's do a couple of numerical examples. I'm running out of time, but let's make sure that we do these two examples. So light with a wavelength of 576 nanometers passes through two slits and forms an interference pattern on a screen 8.85 meters away. If the linear distance between the from the central fringe to the first bright fringe above it is 5.36 centimeters, what is the separation of the slits? So what do we have and what do we want to find? We know that the wavelength is 576 nanometers. We know that the screen is 8.85 meters away from the slits. And we know that this first bright fringe is 5.36 centimeters above the central fringe. That is actually Y1. If you remember the Ys that I listed in one of the slides, this is actually Y1. That's the location of the first bright fringe. So I have these. I want to find the distance between the slits, which is D. I'm going to give you 1 minute and see 1 minute and see if you can put your answers for me in this uh, Nearpod app. Still haven't gotten any answer. I got 1, 2. Very good. Some of you actually gave me the answer. Looks to be correct, but since I'm a little bit out of time, let me actually tell you how you can find it. Note that the formula that I had for Y1 was lambda L divided by D. This comes from that M lambda L divided by D. M is 1. That's for the first bright fringe. So what you have to do, you have to solve for D. So that's going to be lambda L divided by Y1. I have converted everything into meters. So I get 9.5 times 10 to the minus fifth meters, which is equivalent to 95 micrometers. So that is one example. Let's look at a different example. I have a two-slit pattern, which is viewed on a screen 1 meter from the slits. If the two third order minima are 22 centimeters apart, what is the width of the central bright fringe? What do I mean by that? The first thing that we need to know is what the meaning of this thing is. So this is the interference pattern. Again, this is the central fringe. I'm telling you that the two third order minima are 22 centimeters apart. What do I mean by that? So if this is the central fringe, this is the first dark fringe on this side. This is the second dark fringe on this side, and this is the third one. The same thing goes from here. So you can say this is the third order dark fringe above the central fringe here. And this one is the third order dark fringe or minimum means dark fringe on the other side. So there are two third order dark fringes or minima, and what the problem is telling you that this distance is 22 centimeters. So you want to use this to find the width of the central bright fringe. Since I'm out of time, I'm going to do that myself. I still have 2 minutes, but probably you don't have time to calculate it yourself. So this is what I'm going to do. If you remember, I labeled these dark fringes with different m's. So I said, let's assume that this one is 0, this one is 1, this one is 2. So for that one, m is 2, and I can use that in the formula for the dark fringes to find the position of that guy. It's going to give me 5 lambda L over 2D, m plus 1/2 lambda L divided by D. And then this one, uh, again, if you remember, this one was m0. This should be m equal to -1, m equal to -2. This becomes m equal to -3, and y prime is going to be -5 lambda L divided by 2D. From here to here, the difference between these two is going to be delta y, which is going to be 5 lambda L divided by D. and that is going to be 22 centimeters. So from here you can say lambda divided by d is 22 divided by 5, which is 4.4 centimeters. But that is not the width. You want the width. The width is going to be lambda L divided by 2d, or 4.4 divided by 2, which is going to give you 2.2 centimeters. Okay, I am done with what I wanted to talk about for this lecture, but for the next lecture, I have to show you just a short simulation. So just bear with me for one uh, more minute. So if you have a situation like that, create a pulse in a string. When the string hits a fixed point, it gets reflected, but as you saw, the reflection was inverted. This is equivalent to a phase change equal to 180 degrees or pi radians. However, if you had a loose end and you started with a pulse, when that pulse hits the loose end and gets reflected, there is no phase difference. It's going to be in the same, the incident wave was above the string, reflected one is also above the string. It's not inverted. So this is something that I'm going to use in the next lecture, and you are going to see part of it in the pre-lecture video. That is, when light hits a hot boundary, then it's going to get reflected, but the reflected light ray is going to have a phase difference equal, a phase change equal to 180 degrees. But if the light ray hits a soft boundary, then it's going to get reflected, but the reflected light ray is not going to have any phase change. This is something that is going to play a very interesting and important role in our next lecture. But that is it for today. And thank you very much for uh, here. If you have any question, please go ahead and ask. Otherwise, we are going to meet again next time on Wednesday at 10 o'clock. Is there any question? Yes, you have a question.
Does it matter where you start m equal to 0?
For the bright fringes, m equal to 0 is for the central one. Okay. For the dark fringes, it's for the dark fringes, you can pick one above or one below the central bright fringe and call it m equal to 0, and then move up and down from there.
Thank you.
Yes. Any other question? Okay, very good. So I'm going to stop this recording. This recording is going to be posted for you, but I will see you all on Wednesday.